Okay, so about induction, the phenomenon has been studied, and there's a relationship between the rate of change in magnetic flux over time, right? Um, and it will have a electromotive force being induced that proportional to the rate of change in magnetic flux. That's what the Faraday's law is about. And then Lenz's law also add a negative sign here. This is very important. This negative sign basically means that the induced electromagnetic force here should be against the change in the flux. So what actually does it mean? What does it mean by against here, and what is the result of electromotive force? Okay, so let's have a look at this one. Basically, when you have a wire and then you have a magnet, like this is a permanent magnet, right? And if you bring the magnet towards the wire, you will see there's a current in here. So you can see that the needle kind of like moving clockwise here, okay? But if you're moving the magnet away, then you observe that the current actually change the direction. Then the needle turns around here, okay? Counterclockwise, which is pretty interesting, right? And then also, if you place the magnet in the opposite direction, like it's not like south here and north here anymore, but this is the north here and this is the south here, then you can see that beginning, if you want to if you are moving this one away here, then you see that the current also showing in this direction. And if as you are moving to the magnet towards the circuit, then it will change the direction again. Pretty interesting, right? So, but if you just have the magnet inside, the magnet stay on inside the coil here, then no current is detected, no current at all here, and also the same in here. Okay, so why so? So actually, everything can be explained step by step. Just remember the Faraday's law that we have just mentioned right here. Look at the first example. When we want to move a magnet towards the coil here, what happened? So as we know that around a permanent magnet, this is the north pole and this is the south pole, then we see that there will be a lot of magnetic field around it, right? Where you can see that more magnetic field, there should be a stronger field, and where the field is really far away from each other, it's less dense and will be a weaker field here. Okay, and basically the field always like go into the south and out of the north. Okay, so here first before the magnet is further away from the coil of the wire. So you can see here what is the flux now. So we could say that each circle here, you see this one? It will have a cross sectional here, right? Let me draw it. It should be something like this, okay? And there's a cross sectional. This is just the area of a circle, okay? Then you can see that, oh, there will be some magnetic field sent through like from this one, right? But actually it's just like some of these sent through. Just like for now, we just see one sent through, right? This one is kind of out. This is outside. It doesn't send through the area yet. So what could happen when we bring the magnet towards the coil? More magnetic field sent through, right? Makes sense, right? So what happened to the flux now? It increased, right? Yep, that's the key. So you can see that when you move a magnet in this position, the north here, the south here, then you can see it there's the flux increases. There are more magnetic field like sent through the area here, the cross sectional of the coil here. Okay, and now we can see that the change in this one is a positive one, right? It's increasing. And now, yes, again, the Faraday's law and the Lenz's law. Let me copy them here, then we can have all of them together here. Or maybe just let me write it again. That will be easier. So we got that the electromotive force here equals to is proportional to the change in the flux over time, but it have to be negative. It has to be against that change, okay? So now we can see that this actually just means that the electromotive force here being induced, it will related, it will like apply a force that can generate a current. It will like turn on the charge on the electron in the current to move, right? That's why we have a current up here. And actually that current also have a magnetic field induced to go with it. You remember the right hand rule, right? Like right hand rule. But actually if you have a current like this, then around this current there will be a magnetic field, right? Just imagine like we are we are wrapping around the current. Then this is the thumb here, point in the direction of the current. Then we have like these here. It's just like the other finger that grabbing the current, right? So these are the magnetic field B. So if this is the induced current, so this is the induced magnetic field. The induced magnetic field from this current, okay? So this is the B induced. And this B induced here should be against the change in the flux. And because the flux had changed because of the amount of change in the magnetic field, right? So you can see that to begin with, we have like before, we got the magnetic field B1 point in this direction, right? It's out of the north, so it's pointing towards the right now. And then we can also see that later for the B2 it's also pointing the same direction, but it's just a longer one because it's stronger, okay? Because we have B2 as a stronger one, then it's longer. So that in order to go from B1 to B2, there should be a change in the magnetic field. And this one should be the change, right? Okay, so you got the change in the magnetic field in this direction. That's why you should have the B induced in the opposite direction, right? So now if you got this one is like in the opposite direction, and now just use the right hand rule again. This time we can have our thumb like this. Then you will have the current wrapping around this one, right? So then this will be the current. Then it should be up like this. Okay, right? So that's why if you zoom in here, you can see there will be a current in this coil. And that's why you can see that current like this way. You see the current going this way, right? This way, this way, this way, this way, in order to match with the B induced, right? This is the current being induced from the change of the flux sent through the wire. That's why you got a current going this way. Make sense? Okay. So now let's do again. So what happened if we moving the same magnet with the north on the right and the south on the left, but then we move it away? Oh, so now first the B will be a strong one, right? So this will be the B1. Okay, and what happened to B2? B2 is the after. After is moving further away, so it means that the magnetic field has become less, right? There are less number of magnetic field lines here sent through the coil here. There are less of them. That's why you can see that to go from this one, then just to this one, then using the vector addition, what is the direction of the delta change in the magnetic field? It should be this way, right? This is like head to tail. So this is the first vector here. This is the second vector here. If we want to sum them together, we can get the final magnetic field B, right? So the head of the first vector align with the tail of the second vector, then the resultant vector, the sum should be from the tail of the first vector to the head of the second vector. So this is the final B, right? Like you should have it like magnetic field B1 plus the change in magnetic field B equals to the final magnetic field B2. This is the initial. Make sense, right? Okay, so again now we see what happened in this case. What happened to the flux? Does it increase or decrease? It, it's decreased, right? This is less, it's decreased. So when it decreases, you can see that the induced have to be against the change. So it will be what? Yeah. So in order to against the change of this one, it will try to support. It will try to support the magnetic field, you know. So in this case, you can see that the B induced will be opposite to the change. Okay, this is a wrong thing. Okay, this one will be opposite. It's always opposite to the change. Okay, it's also opposite to the change in the magnetic field. Okay, so if the B induced is this way, this is the B induced, then what is the induced current? Yeah, now just use the right hand rule again, and then you should have like the thumb point in the direction of the magnetic field B, right? And then you will see that your hand will just like go in this direction, right? That's your right hand rule. So then now you have that this current this time would go this way, right? It should go this way. So that's why this time you got the current moving around like this. So see, the direction has changed. Okay, but the thing is that the induced always opposite to the change in the source. The key thing here is that you can see in the first case, when you have the flux increasing, the induced actually point in this direction, right? So it's opposite to the original source. You see, it's opposite because it's again the change, okay? But in this case, when the flux decreasing, you see, now it will be support. It will support the original source because it wants to help this one to increase again. Make sense, right? So pay attention to that. You are always have the B induced in the in the opposite direction with the change. Okay, always opposite to the change. But in this case, when the flux increasing, it will be opposite to the B source. Okay, it will be, let me write it down, then you can have some note here. In this case, you can see that it's opposite to the B source, to the, oh my god, okay, it will be opposite to the B. Oh, let me have it the same color like the purple colors. Okay, it will be opposite to the magnetic field of the source, right? But in the second case, if the flux is decreasing, then the B induced will be supporting the source. Okay, then it will be in the same direction of the source. Make sense, right? You can see that. So just distinguish, okay? Distinguish between the difference between the delta change in the magnetic field B and the B itself and the induced magnetic field B. Okay? Sounds good. And then in the next video, we will continue for the last these two, okay?